Hello, chemists. This is Ms. Placino, and you're watching lesson 11.4 on equilibrium expressions. Today we're going to talk about how to mathematically determine if the forward or reverse reaction has been favored at equilibrium. Today's lesson is going to involve a fair amount of calculations, so make sure you have a calculator handy. Goals for today's lesson. You should be able to write general equilibrium expressions. You should be able to calculate equilibrium constants for a reaction when provided the concentrations at equilibrium. You should be able to describe the relationship between K and what reaction has been favored at equilibrium. And finally, we're going to use the equilibrium constant to find concentrations of a substance when it is at equilibrium. So all of these goals, are pretty important for today's lesson. So lots to do today. Let's get started. Before we dive into any new material, we know that we're going to be looking at reversible reactions, reversible systems. Please keep in mind that arrow does not mean at equilibrium. It simply means that this process is reversible. In order to establish equilibrium, we have to make sure the system is closed so nothing can get in or out. We want to make sure that temperature and pressure are held constant. If we are playing around with those conditions, we're going to move equilibrium. And the system just needs time to reach equilibrium. Once you start to play around with any of these factors, you open the system and you either add or remove some of the products or reactants, you change the temperature or pressure, you don't give the system enough time to reach equilibrium, you have disrupted things and you really can't apply what we're going to talk about today. So we're going to make the assumption that all of those conditions have been met and we are definitely looking at a system that is at equilibrium. When we go to calculate the equilibrium constant, essentially what we do is we take the concentration of the products in terms of molarity divided by the concentration of the reactants, also in terms of molarity, and that is how we'll get Keq. There's a little bit more to it than this, but I just kind of want to start with this basic idea initially. If you think about it, there are three mathematical possibilities for Keq. It can be greater than, less than, or equal to 1. It, of course, can't be a negative number. We don't have negative concentrations or negative molarities. So let's think about what that means. What does it mean if Keq is less than, greater than, and equal to 1 in terms of the quantities of products and reactants? All right. If we've got Keq less than 1, that means that we must have more reactants than products. The only way to get a number less than 1 is for the denominator to be greater than the numerator. This means that the reverse reaction was favored. In other words, at equilibrium, we happen to have more reactants than products under the given set of conditions, so the reverse reaction has kind of been the dominant one. If Keq is greater than 1, what does that tell us? Well, more products than reactants at equilibrium, so the opposite. In this case, the forward reaction must have been favored. We produced more products than reactants, so forward reaction is the dominant one. And finally, if you've got the situation where Keq is equal to 1, we must have equal concentrations of products and reactants, so neither reaction was favored. Relatively uncommon, but definitely possible. More likely than not, you're going to have one of the two reactions favored. Let's try to kind of apply this really general formula with hopefully a straightforward example. We're given a system at equilibrium. As simple as it's going to get. A is in a reversible reaction with B. I know at equilibrium, I've got these concentrations. A is 0.2 molar and B is 0.02 molar, and I'm going to try to find the Keq. So I've got that general idea that Keq is equal to the concentrations of the products divided by the concentration of the reactants. If you're looking at this and you're saying, well, it's reversible, so technically aren't both A and B both products and reactants? Yes, you are right. But remember, the convention is everything to the left of the reaction arrow is going to be a reactant. Everything to the right of the reaction arrow is a product. I'll be using that convention all of the time when talking about reversible systems. I know my equilibrium concentrations. B, which is my product, 0.02 molar. Those brackets mean molarity, so I can leave out my unit. and A is 0.2 molar. Now, you probably didn't need to calculate Keq to determine which of these two reactions for the reverse is kind of favored at equilibrium, but why not? We'll go ahead and do it. Keq is equal to 0.1. That means the reverse reaction was favored. And we know that because there are more reactants than there are products at equilibrium. Let's make things a little bit more complicated. Highly unlikely you're going to see too many systems quite this simple. You're more likely to see an equation that looks something like this. M and N are our reactants, P and Q are our products, A, B, C, and D are all coefficients. This looks a lot more realistic. Multiple reactants, multiple products. The general idea is still the same. Keq is equal to the concentration of the products divided by the concentration of the reactants. But now we've got to deal with those coefficients. You can see that the coefficients become exponents. So it's still the concentration of my products, in this case P and Q, but we'll take our coefficients and we'll turn them into exponents. So P to the C power times Q to the D power, that is the concentration of our products effectively. Kind of the same idea in the denominator with the reactants. Please make note, we only include gases in the Keq expressions. We ignore solids and liquids. I'll talk about what to do with aqueous solutions later. Solids and liquids are going to be pure substances that are always 100% that material. For example, water has a concentration of 55.5 molar. It is not going to change in any meaningful way over the course of a reaction, so it will be ignored. We only look at gases. Let's try to put this into practice. Let's head over to the practice problems. All right, let's take a look at reaction number 1. We've got nitrogen and hydrogen in a reversible system with ammonia. So we're asked to write the Keq expression. That is basically to put products over reactants and keep numbers out of it, with the exception of those coefficients turning into exponents. So I would write Keq is equal to the concentration of my product, in this case just ammonia, NH3. Oops. I see that coefficient of 2, so I will raise it to a power of 2. Same thing with the reactant side. N2, no coefficient, times H2 to the third power. That is the equilibrium expression, or the Keq expression. Next, we're asked to solve for Keq. So we want to go through and really just fill in the numbers. Got my concentration of ammonia at 0.020 squared, and the concentration of N2, 0.4, and H2, 0.01 molar to the third power. Go ahead and grind through the calculation. Once you finish your calculation, you should come up with, in this case, a Keq equal to 1,000. So under the given conditions like temperature and pressure, the forward reaction is heavily favored. We have way more products than we do reactants. Good news for those of you who are kind of continuously forgetting your units, Keq is a unitless value, so you do not include units in this case. That's it. I would just say Keq is equal to 1,000, therefore the forward reaction has been favored. Definitely try out the other two questions that we've got here that are really similar in nature and get used to that process of Keq expression. Plug in without products over reactants with the actual compounds and elements themselves. Coefficients become exponents. Then you plug in to solve for Keq. And finally, once you've got your value, you can determine which reaction has been favored at equilibrium. I want to make things a little bit more involved. And I think it's easiest for me to stay in Drawboard instead of going back into the PDF, back into the PowerPoint. So let's scroll up and let's check out these ICEbox things. So we're given this equation. We've got hydrogen and iodine reacting to form hydrogen iodide. We're asked to find the equilibrium concentrations when the initial concentration, that's what that little subscript of I means, of H2 is equal to the initial concentration of I2, and it is 0.2 molar, and we know what the Keq is. We definitely can't plug in the way we just did with the problem with ammonia. We have initial concentrations, not equilibrium concentrations. And we also don't know the equilibrium concentration of hydrogen iodide. So this is definitely a more complicated problem. I'm going to show you how to solve problems like this using what's called an ICEbox. And the ICEbox, that kind of have this like 4x4 grid, is really just a tool to help you organize equilibrium problems. Right. So when it comes to how to use the ICEbox, we'll just kind of put all of this together, and then we're going to go back and apply it to that problem with hydrogen and iodine. We're going to write the balanced equation in that top row, and we're going to put each of those substances in a box. So we'll leave the gray one alone for the time being. We know that we've got H2 plus I2, and it's yielding 2HI. Again, we're only going to pay attention to gases. If we look back at the problem, we can see that all of those substances are gases. To save myself a little bit of writing, I'm not going to include the phase in my ICEbox. There'd be no problem, though, if you chose to do so. In the leftmost column, we're going to write initial, change, and equilibrium. Let's go ahead and do that now. Initial, change, equilibrium. This is why they call it an ICEbox, ICE. These are going to represent the concentrations of each of our substances, our reactants, and our product as the system progresses towards equilibrium. Okay, so now we're set up. Now it's time to start filling out our boxes with some numerical values. We're going to use the information provided. To fill in the concentrations for the initial row. So if you look back at the question, we're told that the initial concentrations of H2 and I2 are equal to 0.2 molar. We're not given any information about the initial concentration of hydrogen iodide, so it's safe to assume that there isn't any present. So I'm going to go ahead and write that information in. No hydrogen iodide. So that is what we are starting with. This definitely isn't at equilibrium. We'd likely have some hydrogen iodide formed as this reaction progresses. In the change row, we're going to use an X to represent the change in concentration that will occur as the system proceeds towards equilibrium. If the substance will experience a decrease in concentration, we're going to write minus X. If the substance would experience an increase in concentration, we'll write plus X. And finally, if any of the substances has a coefficient in our balanced chemical equation, and include that coefficient with the X. So let's try this out. We'll put this in a different color. So I've got hydrogen and iodine to start, and I know I'm going to be producing HI. Well, it looks like the forward reaction can definitely progress in this case, since I've got starting material, my reactants. The reverse reaction can't happen, so I can't lose any more hydrogen iodide as there's none present. So it seems likely, as we progress towards equilibrium, we're going to lose some amount of hydrogen. We're going to lose some amount of iodine. And we should be creating or producing some amount of HI. Hydrogen iodide has a coefficient of 2, so I'm going to include that with the X. That's really all it means. All right. Now finally, in the equilibrium row, we're going to really just add or combine the initial and the change rows together. So different color again. I basically have 0.200 minus X for hydrogen at equilibrium, at the same concentration for iodine at equilibrium. And then each I should be 2x. 0 plus 2x is, of course, just 2x. All right, so this is kind of the use of the ICEbox. And now we're going to take our equilibrium values. We're going to try to deal with this in a Keq expression. All right, so I'm going to come back to 6 and 7 in a moment. I want to tie this back into Keq. So I know that Keq, in this case, is going to be equal to the concentration of my products to the second power divided by the concentrations of my reactants. I've got my concentrations at equilibrium, and I have my equilibrium constant. So let's start plugging in what we know. Keq in this case is equal to 64.0. I know that Hi, 2x squared. And I know that both hydrogen and iodine are going to have the same concentration. So I'm just going to turn that into a squared term. Hopefully so far so good. I've really just taken my equilibrium concentrations and I've plugged them into my Keq expression. All right, now it's time to show off your math skills. What should I do so that I can solve for x? Fortunately here, you might notice that we have perfect squares. I can take the square root of both sides, and I can end up with 64 square root is 8, 2x over 0.200 minus x. So I've got 0.8 times 0.200 and 8 times negative x. So I can kind of just turn this all into 1.6 minus 8x equals 2x. And if I solve for x, since 1.6 is equal to 10x, 1.6 divided by 10 gives me 0.16. All right, so we've found the value of x, and since we're talking about concentrations, this is 0.16 molar. One common mistake that I see when students are solving this type of problem is that they are so excited to have an answer that doesn't seem crazy that they just stop working. You have figured out x. What do you need to do with x in order to find the equilibrium concentrations? We've got to go back to our equilibrium line and our ICEbox, and now we can plug in for x. This is a crucial step that often gets kind of omitted because students are a little bit careless. So the concentration of H2 at equilibrium is going to be equal to the concentration of I2 at equilibrium. And that'll be equal to 0.2 minus 0.16. So they'll be equal to 0.04 molar. And our concentration of Hi at equilibrium is going to be 2 times 0.16, so 0.32 molar. That is my final answer. Oof, lots of work to do on questions like this. Just to kind of finish up, we'll go back and fill this stuff in at the bottom. Plug into the equilibrium expression. Or the Keq expression with the values from the equilibrium row and solve for x. That was in our case, 0.16 that we calculated. Last step, take the value that you've calculated for x and plug it back into the equilibrium row to determine the concentration of each substance at equilibrium. Oops. And these questions are more advanced and can get, very involved very quickly. This worked out nicely, relatively speaking, with 64 being a perfect square. If you don't have a perfect square, you would end up solving the quadratic equation. Before you start stressing out about that, don't worry, I would never ask you to do that on a quiz or a test. We'll leave that for like AP Chem and more advanced classes. But for the time being, you can go through that whole process using the ICEbox to organize your work. Solving for Keq, being able to get equilibrium concentrations. I would say you are way ahead of the game for your average intro chemist. All right, I know this lesson ran a little bit long. Sorry about that. Thank you for tuning in, and I hope you found this helpful.